Hi guys, Dr. B here. This is topic 1.5 for AP Chemistry, Atomic Structure, and Electron Configuration. So this also should be reviewed as well, some of it at least. The objective is to be able to represent the electron configuration of an element or ions using the Aufbau principle. So you'll notice here on the bottom there's something called force due to Coulomb's law. Whenever I refer to Coulomb's law, that is a concept you need to be able to understand to be successful in AP Chemistry, the test, etc. Atoms are made up from protons, neutrons, and electrons. You should know that already. Nucleus contains protons and neutrons. Electrons move around the nucleus. Most of the mass comes from the protons and the neutrons, but the volume will come from the electrons. The electron configuration is a way of describing the arrangement of electrons within an atom, and it's predicted by using the quantum mechanical model of the atom. Excuse me. The inner electrons are called core electrons, the outer ones are called valence electrons, and we've talked about valence electrons before. So these four quantum numbers, it's a basis to be something you need to understand, but luckily for the AP Chemistry exam as of now, you don't need to be able to use the exact numbers to assess what type of atom it is, etc. But something you should know. Lowercase n is the principal quantum number. That's the distance from the nucleus. So it corresponds to like how many orbitals away from the nucleus, like 1, 2, 3, or 4, like looking at the periodic table. L, the angular quantum number, is the shape of the orbital, SPDF. The magnetic quantum number is the orientation of the orbital, different orientations for that. And the spin quantum number is the spin of the electron, if it's up or down, quote unquote, so positive or negative. So when in each little orbital you have two electrons that can fit there, and they have to be in opposite directions, up and down. There are four different cloud shapes that describe the electrons are most likely are going to take. Sorry, I bet. Four different cloud shapes that describe the space electrons are most likely to occupy. These are called the orbitals. There are four letters, S, P, D, F. The S is a sphere. P looks like two balloons together. I guess it looks like a cursive P. There goes. The P orbital can be oriented in three different ways. Each orbital can fit two electrons, each with a different spin. That's one of the quantum numbers we talked about. So yeah, again, just giving you little bits and pieces we need to be aware of. So you have your energy levels, like 1s, 2s, 3s, 4s that we've talked about before. Here, each energy level, there's a specific number of electrons that can be held. So in the s orbital, you can only hold two electrons. Notice how the principal quantum number is how many orbitals there are. So if you have the s orbitals, you can have two electrons each. In the p orbitals, you have up to 6. In the d orbitals, you have up to 10. And in the f orbitals, you have up to 14. And on the side, it says the number of electrons that's on each. In s plus p, for example, you have 8 electrons in the principal quantum number for 2. You can have up to 18 for the principal quantum number of 3, etc. Electron configurations describe the model by showing the shells, energy levels, and orbitals. You don't really need to fill this out like you did sophomore year, but that diagram should look familiar. Coulomb's law. This tells us that the force between charged particles is proportional to the product of the two charges, and the force is inversely proportional to the squared radius between them. So you may have seen something like this in physics for gravitational force. That's actually kind of the same law, so to speak, but in different terms. So the attractive force between two charged particles, it is proportional to the charges, the product of the charges, and then also the inversely proportional to the squared radius. So, for example, if you were to have, let's say you have two atoms you're comparing. Greater charges like let's say that there's atom 1 and atom 2. And atom 1, there is specific charge, let's say, I don't know, I'm just giving generic numbers, but let's say a charge of 3 times 3. That's not even remotely right, but it's fine. In charge in the atom 2, there is 3 times 4, for example. And the radius is the same between in each atom. So in atom 2, the greater amount of charge, that would say that atom 2 has a greater attractive force compared to the other one. So again, it's just a mathematical relationship. If I were to increase the radius between, let's say, my nucleus and my electron, by increasing the radius, the further away it is from a nucleus, the electron will be, that is saying that there's going to be a less attractive force. Electrons that are on the valence shell, the outermost electrons, experience less nuclear pull because the electrons that are in the core of the atom block or shield the attraction of the nucleus from the valence electrons. And so going back really quick to Coulomb's law, that's something we're going to have to review and something we need to understand. And it's going to be your best friend, especially if you see it in the FRQs. I don't know if you can hear the dryer, the washer finish. Off-bow principle means to build up, so you start off at the lowest sublevels and work up. Hund's rule, each sublevel should have 1 electron before being doubled up. Pauli exclusion principle, no 2 electrons can have the same set of quantum numbers, meaning that it has to have opposite spins. So this right here, the 1s2, 2s2, 3p, 1s2, 2s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Again, we'll go through this quickly, but you should be able to do this. How do you write the electron configuration really quick? So you start off at 1s2, or 1s, and then you move up from there. The letters indicate the subshells, the numbers at the top, the superscript numbers, that's the number of electrons in each subshell, and the large numbers, the numbers in the front, that is the orbital they're found on. Yeah, so if you're to fill up it in an energy level diagram, you start from the bottom, work your way up, show electrons as arrows, start off with the up arrow, and the one next to it will be a downwards arrow. When you're doing this, remember that you're starting off from the bottom, that's off-thought principle. Show that, if you'll notice here, in the 2p, notice how there's 4 electrons, but they did not pair up in that second suborbital. So what they did was that they used one of the rules in order to make sure that each suborbital has 1 electron, and then you pair up afterwards. So according to Hund's rule, when you have 3 or more in the same subshell, you put 1 arrow in each box, or each line, I'm sorry, and then you make them share a line afterwards. And this is just mentioning the same thing, but looking at this, this is actually for nitrogen, the 1s2, 2s2, 2p3. One correct way to fill out the energy level diagram, one is the incorrect. The first one, the reason why this is correct, because it follows Hund's rule, and the general idea with this is just something we have to kind of know, memorize, if you will, or just know. The reason why this works out is because it minimizes electron to electron repulsion. That means that there's a more stable, lower energy in this orbital. However, here, I guess the way to look at it, because you could have 1, 2, 3, by kind of pairing this up initially, it creates an unbalance. It creates a electron to electron repulsion that would indicate there's a higher energy. It's less stable, more erratic. Think about some of your classes, maybe, I don't know. All right. Noble gas shortcut electron configuration. You use the noble gases here. The one that's highlighted in red. You use those to kind of create a shortcut in order to make it easier on you. Sometimes a question is going to say, what is the noble gas configuration? What's the full configuration? If it doesn't specify, you don't have to do the you can do the noble gas, but it has to be it has to specifically say it can say give the noble gas configuration, or just give the configuration. If it says give the full electron configuration, then you have to give the full one in order to receive credit. So like, let's say we want to get the noble gas configuration for sulfur. So we backtrack until we hit a noble gas, I'm sorry. Because you can't go forward to argon because you are incorporating electrons that do not exist in this element. So for sulfur, we backtrack until we hit neon. And then we will say, okay, so we have neon. And then, so that's, well, I guess hydrogen's up here. Hydrogen. So on the way, that's crazy. So 1s2, 2s2, 2p6, 3s2, 3p4. So we have 3s2 for here, and then 3p, 1, 2, 3, 4, 3p4. So they want us here to put the number of electrons that are in neon, so that's going to be 10. It's kind of like adding it up. It should equal 16, which would be the number of electrons in sulfur. 16, not 18, my bad. Write the ground state electron configuration for arsenic. So arsenic has 33 electrons. So we're going to write out let's do the full one, just make it easier on ourselves. So looking at your periodic table, hopefully you have it in front of you. You should. So we have 1s2, that is hydrogen, helium, then 2s2, lithium, beryllium, and then boron to neon is 2p6, sodium, magnesium is 3s2, aluminum to argon, it is 3p6, then potassium, calcium is 4s2. Remember that when you get into the transition metals from scandium to zinc, that's technically on the third orbital, 3d10, but it has a higher energy level. Then you go to 4p, so gallium, germanium, arsenic. That's what I want, arsenic. So 4p3. Write the electron configuration for a calcium ion. So if it's an ion, that means that it lost or gained electrons. So if you have a plus ion, that means you lost electrons. If you had a negative ion, that means you gained electrons. So you have to know what is the configuration for calcium. And looking at the periodic table, if you lost 2 electrons because you have a 2+ charge, that means you kind of go up back into the third level. So it ends up becoming 1s2, 2s2, 2p6, 3s2, 3p6. Because initially, the regular calcium, if you will, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So by losing 2 electrons, you don't have the 4s2 anymore. You only have up to 3p6. All right, if you have any questions, please let me know. Hit that like and subscribe and all that. Thanks. Bye.